So we've already seen in the course that everything that we have studied, and indeed everything that we will study, is the result of a relatively small number of building blocks and a relatively small number of assumptions or postulates that we make about the structure of geometry. And even talking about parallel lines, we just use the basic building blocks of lines and the simple objects of angles to talk about parallel lines, how we know that lines are parallel, and the consequences of parallel lines. It also relies on the postulate that we've talked about, that the intersection of two lines is a point. If it weren't a point, we couldn't create angles with a vertex at the intersection, and we couldn't talk about corresponding angles, alternate interior angles, alternate exterior angles, etc. Well, there's one additional postulate that Euclid proposed many centuries ago. It often goes by the name of the Euclidean postulate. It deals with a line and a point that's not on the line. Now, this isn't an assumption we need to make. There are points on a plane that are not a part of another line. This is just something we know to be true. And so what the Euclidean postulate says is that if you have a line and a point not on the line, then it is possible to draw one and only one line parallel to that point, or parallel to that line, through the point. We can't draw multiple, but it also says that we can draw one. And the statement of the Euclidean postulate says, given a line and a point not on the line, there is one and only one line through that point that is parallel to the original line. And this should make some intuitive sense, because if there were multiple lines that went through that point that were parallel, well, then they would all be parallel to the same lines, and yet somehow they would all be intersecting. So there's something that is based on our experience of the world that says there should be one and only one parallel line through that point. It turns out it's called the Euclidean postulate because it is a postulate. It's something we assume to be true, but we don't prove. So go ahead, pause the video, write down the definition of the Euclidean postulate here, as well as any part of the diagram that is helpful for you to understand what we're talking about. Here, I'll draw that parallel line here again. Come back when you're ready to move on. So related to the Euclidean postulate is something that you might call the Euclidean perpendicular postulate, even though Euclid himself didn't actually put this particular postulate down on paper in the same way or with the same importance that this Euclidean postulate, or sometimes called the parallel line postulate, was. But the perpendicular version of this would be, given a line and a point not on that line, there is one and only one line through that point that is perpendicular to the original line. So go ahead, pause the video, write down the perpendicular version of the Euclidean postulate, come back when you're ready to move on. So again, this makes a certain amount of intuitive sense, because it wouldn't make sense for lines that are perpendicular to the line to all go through that same point. That would sort of bend our experience of reality around us as it relates to parallel and perpendicular lines. And then you'd end up with lines that are perpendicular to the same line but intersect and aren't parallel. So all of this should make an intuitive sense. Well, it turns out that the Euclidean postulate specifically, the one dealing with parallel lines, actually helps us with one of the things that a lot of people remember from geometry. If you ask people who have taken geometry what they remember about triangles, or if you ask lots of people who have studied or are close to studying geometry what we know about triangles, there are two common things that pop up. One is that triangles have three sides and three angles, which is true, that is how they're constructed, and the other is that the angles in a triangle add up to 180 degrees. But the fact that the angles in a triangle add up to 180 degrees isn't necessarily an easy thing to show unless we have the Euclidean postulate. And so we're going to use the Euclidean postulate to prove what we call the sum of interior angles for a triangle, and that's that the measure of angle A plus the measure of angle B plus the measure of angle C is equal to 180. And this proof is going to happen on this video, and I'm going to ask you, as we're going through the proof, to copy down the triangle diagram there, as well as the statements and the reasons, because it involves a new strategy for proof that we haven't seen yet in any of the work that we've done, and that is a strategy called construction. So as we're getting started with this proof, there's not really a given to be added here, because our given is that ABC is a triangle, and that's it. And because we have the diagram there that ABC is a triangle, and there's not any extra information, this is not a right triangle, this is not a triangle with any particular size angles, it's just a generic triangle there. There's nothing to add for the given. Now the step of construction is where we add something to a diagram that has one, or sometimes we're allowed to have two particular characteristics. We can state a point that it goes through, and one characteristic related to it. So the Euclidean postulate tells us that we can add a parallel line through a point not on the line. So we're going to add a line through point B called L that is parallel to AC. L parallel to AC through B, and that reason is because of either construction, which I'll just abbreviate to construct here, or you can also call it the Euclidean postulate, because the Euclidean postulate tells us that we can construct that. Well, great. Now we're going to number these angles just for the sake of ease here. Angle 1, angle 2, angle 3. Great. Well, now we have some parallel lines. Line L is parallel to AC, and we have some transversals of those parallel lines. We have AB as a transversal, and we have BC as a transversal, which means because we have parallel lines involving transversals, we can say something about the relationship of the angles that are made. So for transversal AB, we know that angle 1 and angle A are actually alternate interior angles. So angle A is congruent to angle 1 by the alternate interior angles theorem. And angle C is congruent to angle 3 by the alternate interior angles theorem. That we know because we have parallel lines. The next thing that we see here, because now we can talk about angles A and C, is that angles 1, angle 2, and angle 3, they all form the line L, which means that the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 is 180 degrees because they form a straight angle. They're not a linear pair. You could call them a linear triplet if you wanted to. That's not really a term that we use, but it works very well in describing it. So angle 1 plus angle 2 plus angle 3 creates 180 degrees, and we have two other angles that are congruent to angle 1 and angle 3. So what that tells us is that by substitution, the measure of angle A, make that purple there because it's that congruence that tells us, plus the measure of angle 2, which is the measure of angle ABC, plus the measure of angle C, which is because of this green congruence, that we can change out angle 3 for angle C, are all equal to 180, and that is by substitution, because we can substitute in for congruent values. So just by putting a line through B that's parallel to AC, recognizing where there are alternate interior angles that are congruent, and then noticing that angle 1 plus angle 2 plus angle 3 makes up that straight angle for the line L, we've just shown that measure of angle A plus the original measure of angle B, angle ABC, plus the measure of angle C is 180. And because we didn't actually specify anything specific about this triangle other than the fact that it's a triangle, that means that all triangles have angles that add up to 180 degrees.